This is the second half of our calibration and pre-processing tutorial. We left off in part 1 with master combined luminance, red, green, and blue frames from our calibration, registration, normalization, data rejection, and combining. Now we're going to be combining those red, green, and blue frames into a master RGB chrominance image. But first we have to register these master frames to the high resolution luminance image. So they're all loaded here in CCD stack. You can see them. We'll select the luminance as the reference and they'll go right back in to register. We'll use the CCD inspector plugin. We will check high precision, align all. We'll see that all the images are aligned. The RMS error again below about 0.03 or so, which is good. We click apply bicubic B-spline and apply to all. And all the frames are registered to the higher resolution luminance. You can actually click on a star and you can see the full width half max of that star for both your chrominance and your luminance data. For example, if your red data are much larger than your others because of the seeing on that night, you could potentially deconvolute just that to bring the size of the stars back in line with the others. What you'll then do is you'll save the data, but you'll save all in CCD stack. You'll give a suffix like REG standing for registration. And then once you do that, all of these master frames are saved as a new file with the RGB suffix .fits, a FITS file. So now we've registered all of the combined images. What we're going to do next is we're going to combine the RGB data into one color image. To do this in CCD stack, you click on Color, Create. We're not going to use luminance here. We're just going to use the red, green, and blue. You'll make sure that these files correspond with the correct color. You'll put in the G2V star weights that we determined in our earlier tutorial on G2V star, and then you'll click Create. It'll ask you to draw an area, generally in a background. Click on Desaturate the background. We're essentially going to make this dark gray. We're going to make red, green, and blue equal in this area. You click OK, and that's the first color image that you'll see of your object. But we're not quite done yet. We have to do a few more things with it. We open up the Adjust Display, and we're going to take this maximum slider, and we're going to slide it to the right, and we're going to make pretty much everything disappear and make sure that the core is only faintly seen. Then we're going to click on DDP, and we're going to move that slider over until we brighten the image. Now we got a nice, brighter color image. And then we're going to do one more thing with the background. We're going to move it to the left a couple of units so that we don't bring the image in with a histogram that's clipped, in other words, shoved up against the black area in the histogram space, so that we have some working room when we eventually go over into Photoshop. When we're done with this, we're going to save the data, but we're not going to use save data. We're going to save scaled data. That's what we just did. We scaled it. This image. And we're going to call it something like NGC 6946 scaled. Where we will be saving it as a 16-bit TIFF file that will be opened up in Photoshop, and click OK. Next thing we're going to do is we're going to deconvolute the luminance. Oftentimes we want to shrink the stars in the luminance image or high resolution data. We might want to sharpen up some fine details like dust lanes and galaxies or tendrils in things like the Veil supernova remnant. So we open up our luminance image. In CCD stack, we'll go to Process, Deconvolute. We're going to let it pick the stars. You see one selection here with the yellow cross. You'll see another selection there. So it's analyzing the shape and size of those stars. We're going to be using positive constraint and the number of iterations anywhere between 61 and 120. If you have a fast computer, this will take all of about 2 minutes. If you have an older, slow computer, not a 64-bit, this could take 40 or 45 minutes. You click Go and you wait. In the end, what you end up with is a deconvoluted image shown here of our original luminance shown there. And since we're all registered, if you double click on a star, you'll see we went from a full width half max, the size of the star of 4.4 down to 3. In our system, these data, we're at about a half an arc second per pixel. So that would make this 2.2 arc seconds for that particular star. And after deconvolution, it would be 3 times 0.5 or 1.5. So we went from 2.2 to 1.5 arc seconds when we deconvoluted these 60 iterations. If you want to, you could just select, let's say, the galaxy and do another set of iterations on the galaxy to further sharpen more details there if you want. That would be a two-stage deconvolution process. So then you save the deconvoluted file, and we're going to do the same type of DDP for the luminance that we did for the chrominance. So we open it up. We slide the maximum slider over to darken the galaxy. We slide the DDP scale to the left to brighten it up, and then we click down on the background a few notches, and we end up with some reasonably bright data. I should add, the reason I like to do this is because this takes care of a lot of steps in Photoshop using curves and levels. We used to do that 5 years ago, where we'd bring the curves up, then we slide the left slider in the levels over, and we'd repeat it over and over again. This pretty well takes care of most of those steps so that you're maybe 80 to 85% of the way stretched out as you enter Photoshop. So this DDP, especially in CCD Stack, the way it does it, is very important and time saving. So again, move the maximum slider over to the right. We move the DDP to the left. We move the background to the left a little bit, and we save the scaled data. In this case, it's the mean deconvoluted scaled data as a 16-bit TIFF file. And now we're ready to go to Photoshop.